Hi guys, in today's video we're going to be taking a look at simple harmonic motion. So particularly today we will look at a situation where we have a spring attached to a wall. So let's go ahead and draw this out. And basically the idea we have is we have some wall in the ground and there will just be this spring attached, and at the end of that spring we will have some box. So what we're going to be looking at today is the scenario where we have pulled this box over by some amount. So we're stretching out this spring a little bit. So let's go ahead and say that maybe around here is where the unstretched length of the spring would be. So we are stretching it out by some distance x. And so this is going to be defined as our x vector. So we have this distance x here. And so then what we want to say is what happens when we let go of this box. And so what we know from class is that this will be oscillating around this equilibrium position of the unstretched spring. And we can see that by recalling Hooke's law, which basically just says that our force this is our restoring force from the spring, so maybe let's label this force of spring, is going to be minus k times our x vector. So this is to say that our force is going to be k, which is a spring constant, which just has to do with the spring itself, and then times our displacement from equilibrium. And so again, this is a vector, so this minus sign just reminds us that this restoring force is always going to be pointing towards this equilibrium position. So as we've stretched this spring out over here, we see our x vector points to the right, so our force will point to the left towards this equilibrium position. And we have the opposite scenario if this object is, for instance, compressing the spring. Our force will then be to the right because of this minus sign. So the minus sign you usually don't have to worry about too much. It just reminds you which direction is pointing towards equilibrium. So we have this scenario. We know this is going to oscillate in what's called simple harmonic motion. And so then the only other thing we want to keep in mind here is that this force here is proportional to the displacement from equilibrium. So that means as soon as we let this go and it oscillates back and forth, the maximum force will occur when this box is farthest from equilibrium. So that's to say whenever it's at its turning points of motion, it's going to have the maximum force. And then similarly, because we know, of course, that F is equal to ma, that is to say then the maximum acceleration of this object as it's going through its motion will also occur at those turning points. Okay, so let's go ahead and look at the problem statement for today. And that reads as follows. A block with mass m rests on a frictionless surface and is connected to a horizontal spring of force constant k. The other end of the spring is attached to a wall. A second block with mass little m rests on the top of the first block. The coefficient of static friction between the blocks is μs. Find the maximum amplitude of oscillation such that the top block will not slip on the bottom block. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. So we see this is very similar to sort of what we've discussed at the beginning of this video. So the one tricky point comes in the fact that we have two blocks now to worry about. So we see that we're sort of asked for the scenario where our mass little m, our block little m, is just barely not going to be slipping on our block big M. And so what we're actually asked for is the maximum amplitude of our oscillation, so that is the case. And so we can just write and sort of keep in mind that what we're trying to solve for is our amplitude in the end. So we'll just keep this in mind. And this amplitude is defined as the maximum displacement of this motion. So that's just going to be basically at our turning points of our motion, the distance from equilibrium that we reach. So that's what we'll be looking for. And one thing we should keep in mind is that we've had scenarios before where we want to sort of look at the case where something just barely doesn't slip. And every time we do that, we want to, at some point or another, we want to utilize our relation that our static friction force should be at a maximum, which is equal to μs times normal force. So we know this is going to come up, so I would go ahead and write that down right away. And then we know we're trying to solve for this maximum amplitude. So now, in terms of our approach for the problem, we want to start here by thinking, when is this block little m going to have the hardest time to be not slipping on the mass big M? And so you can come to an answer on your own, but you should sort of see that that will occur whenever this system itself has the greatest acceleration. That's when it's going to be hardest for mass little m to stay with mass big M. And so basically we are going to want to look today only at the scenario where this system will have a maximum acceleration. So if we remember from the beginning of the video, of course, we know that our amplitude for Hooke's law, for our restoring force, so let's call this the spring force, is going to be equal to k times x. So I'm only looking at the amplitude. Again, remember the minus sign just tells us the direction we're pointing, so I'm not going to concern myself with that direction right now. So this is going to be equal to kx. So again, as in the beginning of the video, this is going to be a maximum when we're at our turning points of our motion. And so another way to say that is we can utilize our amplitude, and that's to say that this will be a maximum at k times our amplitude. So we want to look at the scenario where this is, the restoring force is maximum, therefore it is k times the maximum amplitude, which is a. So let's go ahead and draw out one of those turning points over here. And so we can, let's just say we have the case where this block is compressing the spring right here. So we know our equilibrium point is somewhere over here, and then therefore our oscillation will look something like this. So this is our scenario. Sorry, we have two blocks here, of course. So this is mass big M, this is mass little m. And so what we want to do now, before we move on, is we want to draw our free body diagram and see where that takes us. So let's go ahead and draw that separately. So this will be mass big M. And then over here, I will draw mass little m. So for mass little m, we see there's really only one interaction going on, which could cause mass little m to have a force, and that'll be the interaction between the blocks. So therefore, our only force here is going to be our force of static friction. So our force of friction will be pointing to the right when this is being compressed. And of course, we know this must be the case because these blocks, assuming that they're staying together as a system, want to move together to the right. So mass little m must have a force pushing it to the right so that it accelerates in the correct direction. And so this is the direction of the friction force. And this can be a little tricky, so make sure if you guys are having any troubles conceptualizing this, go ahead and pause the problem and think through why this must be the case here. So this is the only force acting on little m, so we can now move on to mass big M. And here we see that we have a spring force, which will be acting to the right. So I will for now just label that as a spring force. And we know the form of this force, right? We know this is at a turning point of its motion. This is when this amplitude is maximum. So our spring force must be equal to k times the amplitude. And again, of course, this minus sign is telling us that this must be directed to the right so that it's pointing towards the equilibrium position. So this here is our spring force. And then we also actually have another force that it's easy to forget about, but you need to make sure you're keeping track of the third law pair of this friction force, right? So this mass little m has a friction force pushing it to the right. Therefore, our mass big M must have equal and opposite frictional force pushing it to the left. So this is very easy to forget about, and make sure whenever you have these problems, if you're drawing one third law pair and it's interacting with another object in your system, you'd better be following that third law pair through somewhere. And so in this case, basically, mass big M is going to have some pushback from this friction force. So these here are our free body diagrams. And so at this point, we can now basically just solve Newton's second law for each of these free body diagrams. So let's go ahead and start for mass little m. And I will do this in separate colors. So I'm going to do mass little m in green here. So this is mass little m. And for mass little m, we only have one force, so this is basically going to be equal to force of static friction. And we again know from here we want this to be at its maximum value. So this should be equal to mu s times normal. And then that should be equal to mass times acceleration. So in this case, this acceleration, of course, is the acceleration of block little m. But in this scenario, we're assuming that this system is moving together as a whole. That's what we want to be solving for. So our acceleration should be the same. It really has to be the same for both blocks in order for these still to be staying together. So I'm just going to write a generic acceleration, and we know it'll be the same for both. So here now we can go ahead and say we know our normal force is pretty straightforward for block little m. There's going to be a gravitational force pointing down, so our normal force will oppose that. So therefore this will become mu s times mass little m times g is equal to mass little m times a. So our masses cancel, and we basically get that our acceleration has to be equal to mu static times g in order for this to be moving with our little block and moving with the maximum friction that we're looking for. So I'm going to go ahead and box this because this is one important result here. So now we want to go ahead and move on to block big M. So I'm going to draw this in red. This scenario here is in red. And so for block big M, we have two forces, but we're really going to follow the same idea. So we have our force of static friction, which is to the right, so that'll be positive. So our force of spring. So this is our spring force to the right. And that'll be minus our force of static friction. And then that's going to have to give us our mass times acceleration. So this is just Newton's second law here. We've done this a bunch of times. And in fact, let me be careful here. This should be equal to big M. So in this case, it's very important to keep track of our m's. One is big, one is little. So in this case, now we, again, as we said at the beginning, we know our our spring force has to be equal to k times the amplitude at this point in time. So we can plug that in. So k times the amplitude. And our static friction force itself also, we actually know from over here even, is got to be mu s times normal. So mu s times m times g. So in this case, again, being very careful, we need our mass to be our little m, because this is our third law pair of this force right here. So it has to be the same in magnitude as this force. Opposite in direction, of course, but the magnitude has got to be the same. So we need our little m. So this right here is our total force. So go ahead and make sure you understand that this is the little m and not the big M because of the third law pair. But once we have that, we can then just plug back in right here. So we have some relation. We know we want A, so we're actually starting to see our way to the answer. So we have one relation. We know mu s. We also know the m's and g. So the only other thing we don't know is the acceleration. But luckily for us, we had just solved for what that acceleration has to be. And that has to be mu s times g. So what we can do is plug in this relation for A right here, and then solve for our big A, which is our amplitude. So doing that, we get Ka should be equal to mu s little mg, I'm just adding this over, plus big M times acceleration, which is mu s times g. And then we can solve this for our amplitude. We can factor these terms together. And we should get that our amplitude is equal to mu s times g over k, and then you add up the masses. So this here is our amplitude, which is to say, to be in our case where little m just barely is not slipping on big M, we would have an amplitude of oscillation equal to this quantity right here. So let's go ahead and review what we've done. We first noted that the top block has the hardest time not slipping at the maximum displacement. Then we drew free body diagrams for this part of the motion for each block. Finally, applying Newton's second law to each block allowed us to solve for the maximum amplitude. Okay, so I hope you learned something about simple harmonic motion and also how to sort of break down these tricky problems. If you guys have any comments on this video or any of the videos, please leave those to the comments link to the right of the video link. And also please fill out the video survey on TED. Thanks for watching.